Swayam Prabha. Digital India. Educated India.
Now we will talk about the actual design process for a bolted connection. So first we will do in this chapter we will basically study how to design a single bolt, and the bolt group design basically we will do towards the third section of this course. So first we need to understand, before we design a bolt, we have to understand what are the different ways a bolt can fail. So the ways are also known as limit states of failure. So the ways in which a bolt can fail depends on what type of loading is applied on the bolt. If the bolt is subjected to shear, there are certain ways in which it can fail. If it is subjected to tension force, then there are slightly different ways in which it can fail. And also there is a possibility of a combined shear plus tension failure, for which there are certain limit states, but the expression is basically more of an empirical nature than actually based on any specific phenomenon. So when it comes to bolts which are subjected to shear, depending on whether the bolt belongs to a bearing type connection or a friction grip type connection. So friction grip type connection, you remember, where the bolts are tightened, are subjected to large pre-tension force so that the plates are held together through friction. So such bolts can fail through slip. So slip would be the failure criterion for such bolts in shear. However, if the bolts are bearing type, right, so the plates are meant to slip, and then the bolt shank is expected to come in contact with the bolt hole, such bolts can fail in one of the three ways. Either the bolt itself undergoes shear failure, otherwise the bolt surface, the shank surface, undergoes bearing failure. Also there is a possibility that the plate hole, the hole of the plate, that can undergo bearing failure. So all these will be covered in the subsequent section. When a bolt is subjected to tension, it can have two different types of failure. One type of failure would be the yielding of the bolt shank. An alternate type of failure would be a rupture of the net section. So we will talk about that also. So first we will start with a bolt which is subjected to shear, and the bolt type is a bearing type connection. So if it's a bearing type connection bolt and then it is subjected to shear, there are two or three distinct ways in which it can fail. So here is a simple configuration which is shown to you. These are the two plates which are joined together with a bolt like this, and then these plates are pulled apart as shown here. And there is a possibility that because of this shear force that is applied on the bolt, the net section of the bolt cross section can fail in shear or rupture in shear. So that would be one type of failure. The other type of failure, by the way, this failure surface may pass through a threaded portion of the bolt or the unthreaded, that is shank portion of the bolt, that we need to consider. In addition to this type of failure, which is the shearing of the bolt, also there is a possibility of bearing failure of the bolt surface, which is marked here, for example. So the surface of the bolt deforms locally and undergoes bearing type of failure, or also there is a possibility of bearing of the hole, which in which case the hole elongates and then there is a local yielding near the bearing surface of the bolt hole. So all these three types of failures are possible. First we will talk about how to calculate the shear strength of a bolt, and the net strength of the bolt will be actually minimum of the shear strength and the bearing strength of the bolt. So when the bolt is subjected to shear force, you can imagine that this is a circular surface, a circular round surface which is subjected to shear force demand, and the shear strength of that surface would be actually given by the ultimate stress in shear multiplied by the cross section area, right? So if this is the cross section area of the bolt, we'll take this cross section area multiplied by the shear strength. Now, you might realize that the plates or the planes where the shear failure would take place in such a situation are very concentrated, are very well defined beforehand. They are very well known beforehand. And in such a situation where the failure is very confined, very restricted in a very small area, we don't use yield stress, but we use ultimate stress. So instead of using yield stress, we would use ultimate stress, FU. But FU is the ultimate stress of steel or the bolt material at in pure tension condition. In shear condition, the strength will be given by FU divided by root 3. Where is this root 3 coming from? Do you folks know? Where is this root 3 coming from? What is the reason for a root 3 factor for shear? The shear strength of ductile materials is very accurately predicted by a criterion called von Mises criterion. Von Mises was the scientist who had developed this method, which can be used to predict the failure of ductile materials in various triaxial conditions. So, according to that criterion, it was observed that ductile materials such as steel, bolt, and bolt material too, they have a yield strength which is approximately 1 square root third part of the ultimate stress in tension. Okay. So now you take the case of this bolt. This is a bolt which is holding these three plates together. Now in this particular case, this plate is being pulled in this direction, whereas these two plates are being pulled in this direction, right? Now we can very easily identify the shear planes in this bolt. So if we look at this bolt, here at this interface, you can see it is being pulled in this direction. At this interface, it will be pulled in this direction. And at this interface, it will be pulled in this direction, right? And there will be intermediate cross sections which would be actually transferring this force from this part to this part, and these planes will be known as shear planes, right? Now if the total force is T, and let's say this is divided equally between the two layers, because these thicknesses are equal, so this will be T divided by 2, this will be T divided by 2. And if that is the case, the force demand on each shear plane, these are the two shear planes I have marked here, the force demand on each of these shear planes will be how much? Take a moment to think about it. This is the middle portion, I'm pulling it by force T. Then this is the other portion, this is being pulled by T divided by 2. This is the other portion which is being pulled by T divided by 2. So how much is the force demand at this shear plane? It will be equal to T divided by 2 at each plane. So each of these two planes will be subjected to a shear force demand of T divided by 2. So in a sense, if the total force demand is T, that force demand has to be met by all the interfaces, all the shear planes which are helping resist that force, right? So what we can do is we can calculate the capacity of one shear plane, second shear plane, and all of them, and add them together. That should give us the strength of the bolt in shear, correct? That is the capacity or the force that this bolt can resist in shear. That T force, that is actually the shear capacity of the bolt, is written as VNSB, where V stands for the shear capacity, N stands for the nominal shear capacity, because we have not used the factor of safety yet, material factor of safety. S stands for shear, and B stands for bolt, which is equal to FU. FU is the ultimate stress of the bolt divided by root 3, that is the ultimate shear stress of the bolt, FU divided by root 3, multiplied by the number of shear planes multiplied by the area of the shear plane. Now there are two types of terms here. One is NN, one is NS. NN stands for the net section area, and NS stands for the shank section area. Okay. So If we are careful enough while designing the bolt, we can actually account for two different cross-section areas. So at the shank area, the cross-section area is slightly larger than the cross-section area that is available at the threaded portion. So we can differentiate between the two, and we can actually individually account for those. It is generally a conservative practice to actually assume that, and instead of taking ns multiplied by as, we also assume it to be equal to n multiplied by an. That is just a simpler approach and a conservative approach as far as design calculation is concerned. Now for ns, it is easy to calculate. If we know the diameter of the bolt, we know as is easy to calculate. If we know the diameter of the bolt, we can calculate the cross-section area of the bolt. That is the cross-section area of the shank. An can be calculated as by assuming that the net cross-section area is approximately 78 to 80% of the shank area. Okay, so I hope all the required inputs are available here. Now, once we know the nominal strength of a bolt in shear, we can divide it with the factor of safety. Now, this factor of safety for a bolted joint in bearing failure or bearing type of a joint is given as 1.25 in table number 5 of IS 800. So you go to IS 800, go to table number 5, you will find the value of gamma MB, which is basically the material factor of safety for bolted joints. You take that factor, which is given as 1.25, divide the nominal strength with that factor, and you will get the design strength in shear. Now one must be mindful that this strength is typically okay for most of the conditions, but there are certain conditions where this strength is not actually accurate, and there are some additional factors which play a role that we will talk about briefly in the next couple of slides. Before we get into the other factors, let us also talk about the bearing type of a failure. So you might remember the first limit state was the bolt shear failure, and the other two limit states were bolt bearing failure and plate bearing failure. So as we had seen, if a bolted joint, if a hole is subjected to shearing stress, it actually translates into the bearing stress concentration near the bolt hole surface, at the bolt hole surface, and then this portion of the plate or subsequent portion or the corresponding portion of the bolt also can yield locally under that stress. Okay, and in such a situation, the strength of the bolt or the bolt hole to resist this load has to be calculated, and that will form the other limit state. The expression for the bearing strength of a bolt is given in clause number 10.3.4 of IS 800. Now here, as you might imagine, if I look at a bolt hole and it is subjected to, there is a shank inside, there is a bolt inside, which is loading this half of the cross section or this half of the shank surface area in this direction. Okay, now basically the parameter that should play a role here is the thickness of the plate, the diameter of the bolt. So that is D is the diameter of the bolt, T is the thickness of the plate, and an empirical factor of 2.5, which basically tells us the effective area which is actually resisting that load, multiplied by some material strength. So if it is the failure of the plate, we would use FUP. If it is the failure of the bolt shank, local yielding, then we would use FUB. Also, if the hole is very close to the edge or if two holes are close together, so if the hole is very close to the edge, its bearing strength reduces. So therefore, instead of using FUP, we would use FUP multiplied by E divided by 3D0, which essentially means is that if your E value is less than 3 times the hole diameter, then it will start interfering with or reducing the bearing strength of the hole. Similarly, if the two holes are close together, then instead of using FUP, we use FUP multiplied by the pitch distance, that is the distance of the holes in the direction of the load, divided by 3d0. d0 is the hole diameter minus 0.25. Okay, so and then basically depending on whichever factor of the four of these governs the capacity, which will be the smallest of the four. So the smallest of the four will govern the capacity. So we will calculate all these four factors. We will take the smallest of the four, and that multiplied by T multiplied by D multiplied by 2.5 gives us the shear strength of the bolt in bearing. So bearing strength of the bolt in bearing. Okay, and again the design strength. So this will be the nominal strength. N stands for nominal strength in bearing. The design strength will be actually equal to nominal strength divided by gamma mb, again the material factor of safety for bolted joint. So we have just gone through the two limit states for bolt failure. One limit state was for the bolts which are subjected to shear and are bearing type. There are two limit states. One limit state was limit state of shear failure, and the other one was limit state of bearing failure. So let us do one example here. Here you can read the example. It is required to calculate the design shear strength of this bolt in double shear. Why am I calling it double shear? Because it is basically one plate here which is connected to these two plates. This is a lap joint type of a connection. So this plate is an 18 millimeter thick plate which is subjected to a force in this direction, and then these two plates which are resisting that force in equal amount, both of them are 10 millimeter thick, and then a bolt is connecting these three plates together. Okay, now if we want to calculate the design shear strength of this bolt, we need to follow the following steps. Some details are given that the bolt is 12 millimeter diameter, M12 grade, and the grade of the bolt is 4.6 bolt. So 4.6 basically means that Fu of the bolt is equal to 400 MPa. Fy for the bolt is 240 MPa. The plate is given to be E250 or Fe410 steel, which basically means that Fu for the plate is equal to 410 MPa, and Fy for the plate is equal to 250 MPa. The bolt is a 12 mm diameter bolt, and the hole is a standard clearance hole. So for a 12 millimeter bolt, we know that the hole diameter would be 12 plus 1, which is 13 millimeters. Okay, now we need to design the bolt. So we know from section 10.32 of 10.3.2 of IS 800, it says that design shear strength of such a bolt will be equal to minimum of the design shear strength in bearing, design shear strength of the bolt and design bearing strength of the bolt. Okay, this is shear strength, this is bearing strength. Now when we are talking about this particular bolt, we have to first check what is the shearing action that is going on. First we will check for the shear strength. So as we have discussed before, in a this kind of a joint, you might notice that there are two shear planes. One shear plane exists here, the other shear plane exists here, right? And each shear plane will be resisting half of the total force. So if the total force is T here, each shear plane will be resisting T divided by 2 force. Okay? So if I want to calculate the total shear strength of the bolt, total shear strength of the bolt will be equal to, we will use section 10.3.3 of IS 800, which says that VDSB is equal to FU of the bolt divided by root 3 multiplied by AN, that is the net cross section area, multiplied by the number of net sections, plus AS, that is shank area, multiplied by number of shank sections, shear planes, divided by gamma MB. Now we know that gamma MB is actually equal to, we know that, by the way, this is for one shear plane. For the two shear planes, it will be equal to, since there are two shear planes, it will be equal to summation of the two strengths. So first we will look at FU, that is 400. We know FU of the bolt is 400 divided by root 3. Then we know that there are two shear planes. Now we don't know exactly what is the length of the threaded portion and what is the length of the shank length. So it is a conservative way of assuming that both shear planes are passing through the threaded portion. And if that is true, we can simply double the net section area. So 2, that means number of net sections are 2 multiplied by the net cross section area. Net cross section area is approximately 78% of the shank cross section area. And what is the shank cross section area? That is pi multiplied by the radius squared. The diameter is 12 mm of the bolt, so radius is 6 squared. So that is the cross section area divided by 1.25. Now we can calculate this. This turns out to be approximately 32.6 kilonewton. So this is the shear strength of this bolt. The bearing strength is slightly more involved. We have to consider two possibilities for the bearing strength. If you look at it, if you look at this bolt, here when this plate is pulling the bolt in this direction, there is a shear plane here. Okay, this shear plane is resisting the entire T force. And also when these two plates are pulling the bolt in this direction, there are two shear planes here. Together they are also resisting force T. So first we need to check whether this shear plane can adequately resist the force, and then we can check whether this what is the capacity of this shear plane. So let me mark them in different colors for ease. So shear plane that is marked, bearing plane that is marked in red is called bearing plane 1, and the ones that are marked in blue are called bearing planes 2. Okay. So we need to check for design strength of both of these. For bearing strength, I'll first work with bearing strength, bearing plane 1. For bearing plane 1 or bearing surface 1, the expression for bearing strength is given as 2.5 VDPB is equal to 2.5 times the thickness times the diameter of the bolt divided by gamma MB multiplied by minimum of these values: FU of the plate, FU of the bolt, FU of the plate multiplied by E divided by 3D0, and FU of the plate multiplied by P divided by 3D0 minus 0.25. So now there is no matter of pitch here because there is only single bolt, so there is no pitch. So this part will be ignored. However, E is the end distance that we need to be careful about, and we need to measure the end distance appropriately based on the force direction. So for the bearing plane 1 or bearing surface 1, the end distance will be this distance 65, which is marked 65 here, right? So we will take for bearing plane 1, we will calculate this values 2.5 times the thickness. So for bearing plate or bearing plane 1, the thickness of the plate is 18 millimeters, the diameter is 12 millimeters, gamma MB is 1.25, multiplied by minimum of FUP, FUB. So FUP for the plate is 410, for the bolt it is 400, FUP multiplied by E divided by 3D0. So E is equal to 65 divided by 3D0. D0 is equal to 13. This is 65. Okay. So 65 divided by 39. It is more than 1. So all these factors are more than 1. The smallest of this is 400. So we will take 400 here. And as a result, this value turns out to be 172 kilonewtons. Okay. That is for the bearing plane 1. However, bearing plane 2 has to be considered too, which basically consists of two plates. So, and actually the minimum of the two bearing strengths will be the strength of the bolt. Again, the same expression 2.5 times T times D divided by gamma MB and so on and so forth. However, let me write it fully, multiplied by minimum of FUB or FUP first, FUB, FUP multiplied by E by 3D0 and FUP P divided by 3D0 minus 0.25. So like the last time, the last term will be not relevant. So we can ignore it because there is no pitch distance here. FUP multiplied by E divided by 3D0. In this case, if you see for the blue surfaces, you might notice that the edge distance or end distance is only 35 millimeters, which is shown here. Okay. So E value is 35 and the D0 is 13. So basically it becomes 35 divided by 39. Okay. FUP is again 410, FUB is 400 and this is 410. We substitute the values again, 2.5 multiplied by thickness. This time we will take the thickness of the two plates. So each plate is 10 millimeter thick. So we will take 20 millimeter total thickness. Diameter of the bolt is 12 millimeters divided by 1.25 multiplied by minimum of 410, 400 and 410 multiplied by 35 divided by 39. Which number turns out to be the smallest of the two? This turns out to be 368 MPa. So we will take 368 and this is equal to 176 kilonewton. Now we have seen there are two bearing strengths. Bearing strength of the two thin plates is 176. Bearing strength of the thick plate is 172 kilonewton and the shear strength is 32 kilonewton. The actual design strength VDB is the minimum of the three. So VDB will be equal to the minimum of the three, which turns out to be 32.58 kilonewton. So the design shear strength of this bolt is